Hello professors, this is the ECE 493 progress report number 2 for blimp UAVs playing aerial soccer game actuation control team. I'm the project manager, Eric Fu, and my teammates are Jose, Will, Yu Hong, Romani, and Kyle. First, we will go over a brief overview of what we are trying to achieve. Due to the COVID pandemic, our goals have been scaled down, but we are still going in the same direction. We aim to have teleoperated blimps that can fly and play a soccer game with the ball against other opponents for at least an hour and have no more than 50 cubic feet of helium in them. We are creating offensive and defensive capabilities that consist of modular features that are easy to take off and put back on. To be specific about our features, for defense, we developed a blimp that wields a net to block the ball or an opponent. For offense, we have some cup and claw designs to manipulate the ball, and we designed a deployable fin to interfere with the control of opponents, essentially making them turn involuntarily. We will go over these features later on in the presentation. Next, we have an overview of our system architecture that we scaled down due to COVID. From this diagram, we see that our design utilizes user input to teleoperate the blimp from a controller. The data is decoded to actuate the motors and servos to provide the desired vertical or horizontal movement. In our blimps, we have a motor, the propeller in the back for forward and backward thrust, and a motor in the center bottom of the blimp to provide vertical lift or descent. Servos direct the back motor for turning. From the project plan, we see that we've generally been on schedule, and we developed our features and had many demos. However, while we do have prototypes for our designs, we do need to refine them to be more reliable. In addition, we may have been too ambitious in our testing schedule because while we have had informal tests, we have yet to formally test our stationary offensive claw, our active claw, our interferer fin, or evaluate our communication module. Scheduling has been a problem due to the nature of classes during the pandemic because some classes have indefinite schedules and some exams are scheduled as needed, and this causes time conflicts to pop up, and unforeseen obligations due to the pandemic are also prevalent, but better communication and accelerated testing and data processing should catch us up by the end of the project. Next, we go into our developed defensive capability, the net-wielding blimp. Essentially, our first design holds a polypropylene net that is parallel to the blimp, with carbon fiber rods at the top and bottom to spread the net. The game size ball is stated to be 24 inches in diameter, so we calculated that the max size of the holes possible to still block the ball, but have a minimum amount of net to be 11.4 inches per side of each hole. But we use a smaller ball of 18 inches during the demonstrations, so we went with a hole size of 8 inches at each side of the hole. We see here the defensive blimp during a demo, which is in the middle, and it's screening the goal and essentially blocking the opponent, which is on the right with the ball, from making a goal, and the hoop on the left. Originally, we had a moving gondola design for up and down motion, but a motor rotating a propeller at the bottom center was found to be more reactive, so we have since adapted this design. We also have an alternative design for the defensive blimp, with the net being perpendicular to the blimp. This design is better for going after an opponent, jamming into the goal so no one can score, as can be seen in the picture on the left. However, it is not as good at screening the goal, essentially going up, down, right, left in front of the goal. In addition, the parallel net seems to give extra stability compared to the perpendicular net. It can be said that both designs are better for different purposes.
For offensive capability, we have several different designs. This is our first passive offensive design, which is the cup mounted on the front of the blimp with glue trap to catch the ball. In a previous blimp flying test from other groups, we found the collision between offensive device and the ball caused the ball just bounce away. So we solved it by using modified bug-catching glue traps, which can disperse the energy and secure the ball. After our testing, the cup could catch and secure the ball successfully. In the same time, the cup is lightweight and modular, which are useful for adjusting the weight of our blimps. However, we find out some problems in the test. The glue traps on the front is easy to stick on the wall while the blimp is flying. To solve this problem, we have some further improvements, such as move the glue trap to the middle of the cap, maybe here or here. The other offensive design we have is the interfering fin. It's a bundled fin mounted on the front of the blimp. The fin has the same modified bug catching glue traps, you can see here, for attachment. When the fin is attached to enemy blimps, it will release and then unfurl. It should cause the enemy blimps to constantly turn. While the fin contraption is only 1.5 grams, this may cause buoyancy change when released. Current testing and demos show us the current weight may be small enough to not cause too much difference. We currently have the blimps be neutral buoyant without the attachment, such that the blimp can rush to the enemy while overloaded, attach the fin, and then be neutrally buoyant for the rest of the game. Currently, the interfering fin is released passively by colliding with an enemy and jerking away. There are some problems discovered in our test. With the same glue trap, we have the same problem as before. The fin is really easy to stick on the wall. Moreover, the fin is hard to release from the container after attached to enemy blimps. Now we are working on making the release more reliable and testing more interfering fin with different shapes. Besides the two offensive designs, we have another active offensive design. These two pictures are the 3D model and the assembled 3D printed offensive parts. The printout box in the right side is the assembled module we are testing, and the left side is a revised version based on our test. To activate the device, the motor in the bucket in the tail can gear the track stick in the middle, which can cause the four large gear on the front revolve, and then the rod on the gears will be open or closed. Originally, the device we designed was used to grab the ball with the rods on the gears, but later we find out this straight roll actually just push the ball away when they were closing. So we changed our thought to shoot the ball with the rods and instead use a sticky pad between the gears to catch the ball, like the revised version on the left side. This is our test of pushing. To improve our current design, we need to print out the revised version with sticky pad and test the proper stress of thickness of pad to balloon to see if can catch the ball and if have sufficient force to push it away. And then we need to mount the module on our blimps for testing.
3D printed parts count. In this slide, we have three pictures. The first one is the tail base as well as the servo holder right here. And in the middle, we have the back motor holder. And here in the right, we have the motor basket for up and down movement. Now we can just mount our back motor to the servo directly for left and right movement, as well as we can just mount the bottom motor for vertical movement up and down. The idea here is just the whole design can be modular, so we can just take it from the one blimp to the other, which is we have the two design, defensive and offensive. In this slide is just the combination of the back tail of the blimp, the modular tail. Here we have the base, and we have the servo holder here to hold the servo, and we have the base motor, and as well as the holder for the motor.
Microcontroller evaluation. So our blimp designs are centered around two microcontrollers. One of them is the ESP32 and the other one is the Raspberry Pi Zero W. Currently we use two ESP32 based designs and one Raspberry Pi Zero design. So the ESP32 has integrated Wi-Fi and dual mode Bluetooth. So with its VLE feature, we are able to interface either with a smartphone or joystick controller. In our case, we're using a PS3 controller just because we found that it is much simpler. With the Raspberry Pi Zero, we can also interface a joystick controller through its built-in Bluetooth. And since we are using Python as a programming language, we can use the Pygame library to enable the joystick functions. The other method is to interface a controller using the Wi-Fi module and using computational key commands for function control. Continuing on with our ESP32, here we have two pictures. This is the top and bottom of our SMD design. This design features two motor drivers. So one driver is used for our tail and altitude control, and the other driver we're using for our offensive claw design, and we have a free slot for any other motor based function we'd like to add in the future. This design also has the CP2102, which is a single chip USB to UART bridge, and the micro USB type B port. This is for programming basically, and we have LED indicators just for power and programming. And after soldering all the components, this actually turns out to be only 6 grams, which is actually pretty good for us since we're trying to reduce the weight so we can compensate for anything we add on later. Some of the problems that we've encountered, however, are that for the programming, the differential pair routing design constraints were not met, so we cannot actually program this board by connecting the Type B micro USB connector. So we require a USB to UART TTL module, which is the one pictured here, and some external wiring. After figuring out how to use this, it is actually quite simple. However, we just have to connect the 4 pins, which are the 3.3 volts, RX, TX, and ground pins, and that's pretty much it, and it functions pretty well right now. For the Raspberry Pi Zero, this is our current design, the one pictured here. Basically, since the Raspberry Pi is a pretty complex design and we are lacking the knowledge and understanding, we cannot actually make a PCB for this. So instead, we just solder the components directly. And like we said earlier, our method of control is interfacing the controller through the Wi-Fi module and using computational functions to perform the functions or to perform the controls necessary.
From very early on, we knew that controllability would be the real secret sauce to making a well-performing blimp. So we spent a lot of time and thought perfecting what that blimp would look like. So for our passive features, to give good blimp stability and controllability, first off, the weight balance is crucial. To have most of your weight on the bottom of the blimp and spread out front to back to make the largest moment of inertia, but also keep the blimp from rolling over. Simple as that. And it makes the blimp perform pretty well. It stays upright and pointed the way you want it. But while it's flying, that gets more complicated. Now we need to add fins or sort of like a cylinder-shaped device, a shroud around the thruster, to deflect airflow as we start yawing or pitching, and keeping the blimp flying straight. Next up, we have active features. At first, we were really sold of the idea of the movable mass, which would be a really efficient way to pitch, or really electrically efficient way to pitch the blimp up and down. But eventually we decided that we could get much better control with a vertical thruster, um, just through trial and error. And the last secret for good blimp controllability is the controller itself. We tried, throughout our prototyping, we tried controlling it through the keyboard, which was just too slow. Smartphone control was faster, but to use a touchscreen was pretty difficult. And really the best way to do it was just a handheld joystick controller, like a PS4 controller, like we're using now. Much better, much easier to control. It's just designed to control things well.
Now we're on power consumption part. As for this section, we tried multiple batteries and we found that the 3.7 volts, 1000 milliampere hour was the best battery to do this, and we conducted 3 different mode tests. Once we verified that, normal or idle mode, which was basically only running the Raspberry Pi or ESP32. For this instant, these numbers are for the Raspberry Pi one, and it was well over 2 hours experimentally. So we found out that it was obviously clearly sufficient for a 60-minute game. Full speed, which or called the run the back motor nonstop until it dies, got around 63 minutes, a little under 62 minutes and 46 seconds. As we found that was the most power consumption, was the back motor that we were using, not the servo or the bottom motor that we used to lift it up. And then a third mode, we had max draw or game conditions, as we like to call it. This only got 52 minutes and 48 seconds, as the game conditions are very hard to experimentally measure, as each game that is played could be different, but we were playing a game that we were defense. So we basically were guarding the hoop and moving to defend to block the ball. So that we got 52 minutes and 48 seconds with that. Obviously, these were experimentally. We have theoretical value, and that as well as voltage, current, and power consumed by each. This section's fun spent in man hours. As you see, there's 5 main parts that we've been doing this semester with testing the blimp stability, controllability, 3D printing those parts to help build the actual blimps that we're using, controlling the ESP32 or Raspberry Pi Zero, mainly ESP32 because we had 1 Pi. Offense and defense capability was the main part that we were trying to drill down, try to get better netting, better offensive stuff to stop the blimps from scoring for defense, obviously. And then demos. As demos, we got there early every week to improve our designs and make sure that there's no faulty equipment or something's wrong before we were trying to actually demo and show what we've completed in the week or 2 weeks. As you see from previous semester, the total man hours and the fund spent. As you see, that fund spent section is kind of expensive with $1,287, but we just started working, so we had to get a lot of the materials that were kind of expensive, as well as and halfway through the semester, COVID-19 hit, so we had to buy some extras. So if someone else wanted to work on it, if we needed like 2 people or 3 people wanted to work on it, we had to get like 3, so then everyone could work on it, since we weren't meeting at that time. And then total hours, you see 364 hours, and the total funds spent is around almost 1,500. As you can see, we spent around $200 for this semester, since we had basically the materials we needed from the previous semester. So the overall cost breakdown of the $1,491 and 48 cents thing. As you see, 3D printer and filament is a big section, as well as the ESP32s and Pi Zeros we bought. Other than that, you see the small sections of motor drivers, blimp kits, back motors and propellers, servos, batteries, wires, helium, netting for the defensive capabilities, bottom motors and propellers, miscellaneous, battery chargers, XBE3, and LiDAR and IMU. As for this, as you see, miscellaneous, that is tape, rubber bands, rods that we use to help make the netting and glue, stuff like that. Was very little. That was essential, though, for making these blimps. As you see, LiDAR and IMU and the XBE3, that's items that we necessarily haven't really used, but we bought earlier as COVID-19. Whenever that, we kind of changed our scope, so we haven't used some of these items, or we improved. That's why the total cost is a little expensive. Now we're going to break it down per blimp cost breakdown. As you see, the total is a little over $110. It's $109.83. But here you have your printed parts, your bottom and your back motors and propellers, your offense capability or defense, depending. Helium, wires, battery, servo, motor driver, ESP32, and blimp kit that we used. As this blimp breakdown is for the ESP32 one we used because we had a Raspberry Pi one, which were run a little more expensive. So add like $15 on that would be around what if you were using a Raspberry Pi Zero. But offense and defense capabilities, as you can see, is pretty cheap compared to the other encompasses of what we had to buy to make this blimp. As a lot of the offense, we just had rods and sticky tape, and defense we have netting, which is pretty cheap, as that is seen by the previous one. Then netting was a very low percentage. Thank you.
Our demonstrations got off to a rough start, but we improved pretty quickly and things got up and running. Our first demo, we were barely able to fly at all once we were able to connect everything together. But demo 2, we came back 2 weeks later and fixed all of the smaller issues and were able to start figuring out how well these blimps would fly around. It was kind of slow at first. We realized that we needed more power, so at the next demo, demo 3, we increased the thrust through software and changed out the motor to make sure we had as much power as we could, and turns out we were pretty fast by that point. We added 2 more designs for the 4th demo, and that's when we first were able to start kind of playing the game, or figuring out what the game will look like at competition. And it really highlighted the importance of teamwork. Our blimps were quick, but it was easy to get confused and lost in the chaos. We tried our interfering fin device and had trouble getting it to deploy properly. But by the next week, we were ready to go, and we blocked some goals. We did pretty good. Not bad. Not bad.
Problems and surprises encountered. We encountered 4 problems: instability of the blimp, our design needed 2 batteries, unexpected behavior of the active offensive cloud, and the planning didn't account for the cluster of the midterm combined with COVID-19 restriction, which impacted our testing and schedule of our progress. In our first testing, we test the stability and controllability of our blimp. The first test, initially the blimp was unstable at all. As a result of we had to remove the fins to reduce some weight. Therefore, the blimp didn't fly in a controllable manner. Also, we test our power consumption. We face one issue, and still we face it until now, that we must use 2 batteries in order to power our motors and microcontroller as well. In our second testing of the blimp, we figure out that we can modify our blimp by using a shroud that can increase the efficiency and direct the blimp to move forward, because the shroud has some advantage as increasing the efficiency, also increasing the limit of the vector thrust that can direct the blimp to move forward. And in the second testing as well, when we test our offensive, the active offensive cloud, instead of grasping the ball, it was just pushing the ball away. In order to do that, we still incorporated to be modular. So we are using some release mechanism. So instead of grasp the ball, it can just release the ball. So, and the first one, since we have COVID-19 and we cannot just go to the campus to test our blimp for control or stability or power consumption, we decided to go to one of our co-member house for meeting every Monday and Wednesday so that it just restrict our testing schedule. In this slide here, our action and a plan. Our action and a plan is to finalize our offensive design and uh, stability and controllability of our blimp. We hoping that we can customize our envelope by using the balloon making machine so that we can make a larger envelope that can carry more helium, so we can put more than 3 fins in each blimp in order to make the blimp stable as much as possible. And the third plan here is to improve our service mounting design PCB board that can incorporate our communication module with testing and communication by using the XB communication, so that way we can just control the blimp far, at least like 30 feet away. Also, we are finalized testing of the offensive and defensive function as well. References. Here in this slide, we have the references that we use throughout the design of our blimp. And that will conclude our presentation for today. And as always, we welcome any suggestion and comment.